Hey everyone, can everyone hear me?
Yeah, good morning.
Awesome, thanks. We'll give it probably 5-10 minutes. Whoops. Hey everyone, we're going to get started in 5 minutes at 6 past 11. All right, everyone, let's get into it. Now, we are recording in Zoom. Yep. We are live on YouTube. Yes. Awesome. Music off. I'll send you guys the playlist at the end of this if you want to find some songs. Okay, so welcome everyone to the Smart Contract Developer Bootcamp. We've got just under 300 people in the Zoom session, and we have a few hundred people in the YouTube session as well. So huge turnout. Congrats to everyone. So whether you realize it or not, we're currently in the middle of a digital revolution. So when the internet first came around and it started to mature, there was this monumental shift in the way that businesses operate and how society interacted with each other and with these businesses. So it changed the way that we work, it changed the way that we play games, how we did commerce, how we socialize with each other, and all of these things. Now that was round one. Now the internet's coming again for round two. And in round two, this time it's coming with blockchain and smart contracts. And once again, it's going to fundamentally change the way that people interact with businesses. But this time, it's going to revolutionize how we conduct agreements with these businesses and with each other. Now, smart contracts have started to really gain adoption in areas such as DeFi, insurance, gaming, art, and all those types of things. And adoption is continuing to rise into other areas as well, as people start to realize how they can take us into this new age of economic fairness, transparency, and efficiency. Now, there's over 26 million developers worldwide across all the programming languages, but there's only a few 100,000 smart contract developers. So we've got this huge up and coming industry with so much potential, but there's actually a massive lack of talent. And learning smart contracts and blockchain is not just like learning, Java or Python or just a normal programming language. There's all these nuances involved and things you kind of have to do that is very different to traditional programming. And what we've done is we've created this bootcamp as an initiative to help you begin your smart contract developer journey, to give you the basics and fundamentals of smart contract development, as well as to teach you about how to create what we call hybrid smart contracts that make use of decentralized Oracle networks. And you'll learn more about those later. So we feel that learning how to use a decentralized Oracle network like Chainlink is actually an integral part of a learning path for a smart contract developer. They enable you to build the really game-changing decentralized applications of tomorrow. And we want to teach that to you. We want you building the game-changing applications of tomorrow. We want you building participating in hackathons, creating and joining startups, contributing to open source projects, all of those things. We want you to be successful with smart contract development. Your success is our success, and we just want you to be successful. So welcome to the Smart Contract Developer Bootcamp. We can't wait to teach you about all things blockchain, smart contracts, and Chainlink. And I'm excited. All our helpers online here are excited. Chainlink Labs is excited. Hopefully you're excited. Let's learn about smart contracts. So my name is Harry Papakrisiou, and I'm a developer advocate for Chainlink Labs, and we work on the Chainlink Decentralized Oracle Network project. I'm joined today by a number of people here who are going to be helping me with this bootcamp. So we've got all of our Chainlink DevRel team here online, as well as we've got some developer experts in on the Zoom call. We've got some community advocates on the YouTube stream, and we're all here basically to help you. So say hi, everyone.
Hi.
Hey everyone, Zach, Dev Advocate here.
Great.
Hey guys.
Welcome. Really excited.
Welcome, everyone.
Now, before we move on,
Hey guys.
let me just check something. So here's an outline of what the schedule looks like. It's split across 3 days. We've actually forked days 2 and 3. So depending on whether you're more familiar with Python or JavaScript or neither, you're going to be put in either what's called the brownie track or the hard hat track. But day 1, everyone's together. We're all going to learn together here. And in day 1 here, we're going to basically give you a basic understanding of smart contracts, the Oracle problem, Chainlink, and some of the tools and features that Chainlink offers you. You're going to get some hands-on experience writing smart contracts, deploying smart contracts, funding them, and doing all those types of things. And then in days 2 and 3, we're going to move on to using other development environments and doing some other cool stuff like working with local developments and testing and things like that. So it's a very varied course. It's not just Solidity here. There's more to smart contract development than just learning Solidity. But what we've done is we've tried to make it a bit of a mix of everything to give you a real hands-on experience of what it's like to be like a smart contract developer, right? So this course won't make you a smart contract professional, but it's a great starting point for then to go on and continue with your smart contract developer journey. So here's how it's all going to work. It's going to be a 2 to 3 hour session today, broken up into sections with some exercises. And generally the flow of events will be there's a presentation followed by some questions that you guys can ask, as well as I'll be doing some demos, and then you guys will be doing some exercises. If you have any questions, you can ask them in the chat, whether in YouTube or in Zoom. If you're in Zoom and you need help during an exercise session, you can put your hand up in Zoom, and we've got a bunch of helpers that will hopefully get around to helping you. And what they'll do is they'll send you a private message in Zoom with like a URL, a link. You click on the link and it will take you to a private session with the helper, and you can share your screen and hopefully they can help you, and then you can come back to the main session. If you're on YouTube and you've got questions, hit us up in the chat. We've got people in the chat there, or in the Developer Bootcamp channel in the Chainlink Discord, and we'll try to help as many people as we can. And if you get left behind, we have to keep the schedule, unfortunately, but at the beginning of the next session, you can always ask for help again, or at the next exercise, and we'll try to help everyone we can. We'll share all the slides and exercises at the end of the boot camp, so anything you miss out on, you can complete after as well. We want everyone to get everything they possibly can out of this boot camp. So just quickly on the exercises for today, we're going to be working in the Remix developer environment. So if you receive some setup instructions, all you'll need to have completed for today is setting up MetaMask and then funding your accounts with ETH and Link. And I know we've had some issues with the faucet over the last few days, so some of you people may not have been successful. If you haven't, we encourage you to go there now or go there during the first exercise. And try the faucet again, and hopefully you can get some Link and ETH into your MetaMask account.
Just
for everything else,
just
that's going to be required for days 2 and 3 of the boot camp.
Yeah, and just a quick note on the faucet.
So just quickly, here's the day 1 agenda. We're going to talk about blockchain. We're going to talk about smart contracts. We're going to talk about Ethereum and Solidity, the Oracle problem and Chainlink. We're going to go into price feeds, how to access APIs, and how to get a random number in your smart contract. So just quickly, before we go on, I'm just going to spend some time going over some important concepts that you need to know as a smart contract developer for when we delve into some of the deeper topics and exercises later in the bootcamp. You can't become an awesome smart contract developer unless you have an idea of how it all works under the hood. And also, we just want to go over why, as a developer, you want to focus on smart contracts. What's the whole point of them? What do they do that's good? And all those types of things. So first, just quickly, let's talk about blockchain. So blockchain is a highly secure, reliable, and decentralized network. So basically, it's just a network of computers that stores data and transactions in a shared ledger that can't be controlled by anyone. And the thing to note here is that most of them actually have what's called a virtual machine as well. So they're actually not just a ledger, but an application platform as well, right? They can run these little applications on them. So for example, Ethereum has a virtual machine to run these simple programs called smart contracts. So just a quick example here that shows two parties performing a financial transaction with each other. So with a blockchain, it's what's called decentralized, which basically means that there's no single person or entity that can directly control or influence the behavior of the network of computers, right? It takes a large amount of effort to do so. Whereas in a traditional scenario, you've usually got a trusted third party in between two participants who kind of want to, in this case, transact some kind of value between each other. So decentralization is kind of split into three aspects. So architectural, how many physical computers is the system made up of? How many of them can the system tolerate breaking down at any given time? Political decentralization, how many individuals ultimately control the computers that the system is made up of? And logical, does the system act like a single monolithic object, or is it this undefined or vague swarm? And how would it act if you say cut it into two, would the two separate sides operate independently or not? So a blockchain is meant to be architecturally and politically decentralized and not generally logically decentralized. So the benefits of decentralization, pretty straightforward: fault tolerance, attack resistance, and collusion resistance. They're less likely to fail accidentally because of the way they're architected. They're more expensive to attack and destroy or manipulate because there's no central points. And it's much harder for participants in decentralized systems to collude, to act in ways that benefit themselves to the expense of others. So I'll just give you a quick demo, which I think is really cool, to kind of go over these points. Hopefully I can find it. Here we go. Let me know if you guys can see that okay and it's not too small. I'll make it a bit bigger. So blockchain does a whole lot of what's called hashing. In the case of Bitcoin, it's a SHA-256 hash. So as you can see, I'm putting some data in and we're getting a specific string with a whole bunch of characters at the bottom. And one thing to note, hashing is just a method of cryptography that converts any form of data into a unique string of text. And you can hash anything. You can hash a piece of string, music, a video, anything you want. And regardless of what you do, one thing to note is that it's always going to be the same length, basically, in this scenario. So, and you can see if I hash my name here, Harry, you can note that if I take away and remove the Y, I'm always going to get the same result. So it's like a one-way street. You can always hash something and know what the result's going to be, but you can't go back the other way. You can't take a hash and then work out what the data was. So that's the beauty of hashing here. So yeah, just an example of hashing something. Let's go and show a block now. So this is just a very simple example of a block in a blockchain. It's got a block number. It's got a nonce, which is just a number. And in this case, we've got a bunch of data that we want to put into the block. And as you notice, the whole thing turns red here as soon as I start putting stuff in. And that's because the hash here is invalid. So there are certain rules that the protocol specifies that says, hey, for it to be a valid hash, it has to do this. So with blockchains such as Bitcoin and everything, and all the ones that use proof of work consensus, they usually require a certain number of leading zeros. I think Bitcoin currently requires 20 leading zeros, but in this browser one, it's just 4. So as you can see, when I press the mine button, it's actually finding the correct nonce value for this block to have the correct number of leading zeros. So there you go. So that's just a simple example of taking a bunch of data or transactions and mining it, finding the correct nonce to find a correct hash with the correct number of leading zeros. So let's move on to blockchain now. So we saw blocks. Here is a blockchain, which is basically just a collection of blocks. And as you can see, each one can have a bunch of different data or transactions or whatever you want to call them. But the thing to note here is that each block contains a link to the hash of the previous block. So the first block here, because there is no previous block, the previous hash is 0. But over here, you can see the previous hash here is actually this number here. And then once I mine this one, you'll see that the hash here in this previous column matches the hash here. So that's how that's kind of how blockchain is kind of formed, and it's got its immutable properties. Because if I go back in time and change something, then the hash of this block changes, which means that the link to this block is broken, which means the link to the block in front of that's broken. So we kind of break the whole chain there by doing that. And if you go and change a block in the past, you need to remine all of the blocks after that to kind of get to the present and kind of take over the blockchain. So generally, the rule is the chain with the most work or effort is the one that kind of gets to be chosen as the main chain. So just to close off this example, we'll just show a distributed scenario here. So we've got a blockchain with just 3 blocks with peers A, B, and C. So for peer A, let's say if I want to put some data in block 3 and mine that. And let's say I now go back once that finishes, and in block 3 of this peer B, I'm going to put something else. And in block 3 of peer C, I'm going to put higher again. So as you can see, the hashes of peer A is 004F4 whatever, is actually the same as peer C because the data is the same. But peer B actually says, no, actually block 3 is, this here, which is different to what the peer A and B have. So the thing to note in this scenario is it's kind of like a little democracy. And in this case, peer A and peer C have more basically, they've got more votes that say, no, actually it's this. So what will happen is that their version of block 3 will be the one that's chosen as the correct block. So that's kind of just a quick overview of blockchain. I hope it makes sense. If you want to read more into it, there's a lot of information on the internet. Now, any questions on blockchain before we move on?
Hey, Harry, can you hear us? Can you hear me? Harry? No, I guess he cannot hear me. I'll try to ping him. Try to ping him elsewhere.
Yeah, I just texted him.
Oh, okay. Harry, you got to turn your volume on, mate.
Just let me adjust my audio, guys. I don't think I can hear you properly.
All right, cool. We got to him. Nice work, everybody. Got some really good questions coming through. While Harry fixes his audio, I'm actually going to take a couple of these questions that are coming in. So a couple of people asked, they said, hey, how big can this blockchain get? That's a great question. And the answer is it's unlimited, right? So somebody said, hey, so this is basically an immutable linked list. That is exactly correct. It's just an ongoing linked list and it could keep going forever and ever and ever. Great question. I'm going to look at a couple of these questions while we wait for Harry here. What does the mine button do? Is it calculating the hash? Yeah, so when Harry's clicking the mine button here, that's exactly what it's doing. It's running that hashing algorithm that we first saw. I guess there's a voting thing that just popped up. Okay. But, oh no, that's a question. Yeah, so when he's hitting that mining button, it's running that SHA-256 algorithm with the block number, the nonce, and all the data. So that's what's happening when he's hitting that mining button. It is calculating that hash. Good question. Harry, can you hear us yet?
He's just adjusting still. So
okay, adjusting still. No worries. Yeah, and so somebody said, oh, okay, so this is cool. Well, what does this do? It means that once you calculate one of these hashes, you actually can't do it the other way around. So you hash the nonce, the data, the block, you get this hash. You can't actually go from the hash backwards, but you can very easily verify that the hash does represent that data. So that's why that's why private keys similarly are so powerful, because they're one way. How is immutability enforced? That's a really good question. So as he was showing there, once these hashes are created, the whole blockchain, it was green, right? The whole thing was green. If you go back and you change something in the blockchain, the hashes would no longer have those 4 trailing zeros, right? They would no longer be valid to solve that problem, and the whole rest of the blockchain would turn red, right? So if you go back and change everything, you then have to change the entire blockchain. And if you change the entire blockchain, as he was showing here, if you change the entire blockchain, all the other nodes that aren't changed are going to basically say, hey, why do you have this crazy weird blockchain? What's going on? And you're going to have this one blockchain that's totally different from the rest of them. So that's how it's immutable, because all the other blockchains are going to reach a consensus saying, well, no, that one outlier is doing weird stuff. Good question. A whole bunch of other questions came. Harry, can you hear us now?
Now I can hear you. Yeah.
Hey, welcome back.
Switch headphones.
Welcome back.
We'll do a couple more minutes of questions, and then we'll have to move on. Any more good questions we can see in the chat?
Someone asked, won't there be many parallel new blocks being mined? Yeah, there are blocks that get mined occasionally. Those are called uncle blocks. And the rate at which the blockchain is appended with new blocks is kind of set to minimize those parallel blocks being mined.
And another good question here. If over 50% of the mining power is centralized, then they can mutate the blockchain, no? So that's a really good question. And that actually is what's called a 51% attack that you might have heard before. So just like what I was saying is, hey, there's this one blockchain, it's the outlier, all the rest of the nodes are going to be like, you're delivering crazy data, get out of here. If 50% of the nodes say the blockchain state is X, then that's what the state of the blockchain is. So yes, if you took over more than 50% of the network, you could basically change the blockchain to be whatever you want. It gets harder and harder though. The more blocks that are mined. Like if you tried to change something from 2 years ago, you would then have to mine 2 years worth of blocks, which is incredibly computationally expensive. So it's really, really hard even if you do that. But yeah, that's what's known as a 51% attack. And yeah, and this is why the bigger your decentralized network, the bigger, like the more nodes are on your blockchain, the more powerful and the more secure and the more reliable it actually is.
Yep. Great. Is my audio a bit better now, Patrick?
Yeah, are you using this is the better mic. You sound good.
Right. Okay. I submitted a poll for you guys in the Zoom, or just a little quiz or trivia question. So what was the original name for the term blockchain as outlined in the first version of the Bitcoin code? So for those in the YouTube session, we had the options were blockchain in 2 words, time chain, chain of blocks, and block linked list. And the correct answer is time chain. So Satoshi actually called it time chain. And it wasn't until Houdini actually called it blockchain randomly in some public correspondence that then in the next version of the code, we saw it change to blockchain. So that was the birth of the term blockchain. So let's move on, guys. Okay, let's talk about smart contracts now. I'm just going to end this poll quickly. So what is a contract and what is its purpose? So a contract is a binding agreement between 2 or more parties, and they started out written on things like stone and paper and things like that. And eventually we moved on to what we call digital agreements now. So the storing and executing of these agreements is done digitally now. And these digital agreements actually underpin many aspects of our lives. So just a couple examples to kind of convey this idea to you. So you've got a digital agreement with your bank that says, you can hold your money in our bank account and we'll give you X savings rate. We'll give you access to your money whenever you need it. You've got a digital agreement with Netflix when you kind of sign up to Netflix to consume their content. You've got digital agreements with all of your insurance companies. You've got digital agreements with the crypto exchange that you may want to buy crypto with. You've even got a digital agreement with this bootcamp when you signed up and agreed to our kind of code of conduct and things like that. So we all have these digital agreements in our lives. And I just want you to think about the relationship that you have with some of these agreements and with these companies and institutions, because one common aspect between them is you've got one of the parties in the digital agreement is actually the same party that's enforcing and executing the agreement and determining the outcome of kind of the agreement, right? And because of this, the relationship that you have with these companies and institutions is not actually what you think it is. It's not kind of one where everything's kind of working well and they always act in good faith. And really, it's actually one of high risk and one where you generally don't get a high level of control, one where you generally have a low level of transparency. And a lot of the time, there's kind of these monopoly rents being extracted by these institutions and platforms. So essentially, it could be considered as kind of a bad deal in many cases. And these agreements are built to favor specific actors, and usually it's the ones that are in control. So these are what we call paper or brand-based agreements, where we're trusting in them, in these institutions and companies to act in good faith. And contracts are kind of underpinned by law, but a lot of the time the law won't always help you because they specifically set up these contracts in a way so that if it came down to law, they can kind of say, look, sorry, see this kind of section of the legal conditions here, it actually means I don't have to pay you. So you and if you go to them and say, oh, sorry, for my insurance contract, can you please change section 3, paragraph 4, delete that, and then add this line instead? Like, they're going to basically tell you, no, go away. And then you'll be forced to either just go with them or go down the road to another competitor where you're going to kind of get the same deal probably. So it's kind of what we call brand-based trust, where they're saying, trust my brand. But if push comes to shove, they can kind of do what they want and take advantage of you if they want, in regards to executing and enforcing the agreement that they have with you. So one good example of this is the existing financial system and how it's skewed to benefit certain better resourced, better informed actors. And everything kind of works well in predictable market conditions where everything's kind of working as it should. And we participate in it because it's the only financial system that we have, and everything works fine when everything's normal. But then when conditions change and certain actors don't benefit that are supposed to benefit, then we kind of find out how the system really works. And in many cases, the system might stop, or the outcome of the agreements that we have in this system act in a way that's kind of detrimental to the average users, right? And there's countless of examples of this happening. More recently, the Robinhood GameStop fiasco, which I'm sure a lot of you would have seen. They had a digital agreement with Robinhood, and it was a bad deal, and Robinhood decided they couldn't kind of trade GameStop on a certain day. So other examples, going back a few years, I was in Greece in 2015. I saw the ATMs being locked up and kind of all the people lining up. It was pretty not a nice thing to see, especially when you see locals kind of going on holiday with their families and stuff and only being able to take out 66 euros per day. Going back a few years before that, Cyprus had a financial crisis in 2013. And if you had savings in your Cypriot bank account back then, you got a 5 to 10% haircut taken on it, I think. So 5 to 10% of your savings were just taken by the banks and the governments overnight. And more recently, I was helping a relative of mine trying to buy some crypto assets. He was trying to get into crypto. He said, hey, can I get some help? And I said, sure. And he signed up to an exchange here in Australia. It was the biggest exchange, regulated, complies with the laws. And because he doesn't have internet banking, he had to go to the bank to kind of transfer some money in, and the bank wouldn't do it. When they found out what he was using the money for, they said, oh, no, sorry, we're not going to do it if it's for crypto. There's a lot of scams and this and that. And, he kind of went off with them. He's like, who are you to say what I do with my money? These are a legitimate exchange that complies with all the laws and everything, and you won't send my money to them. So once again, these agreements are foundationally built on brand-based trust. And these types of things will continue, and they'll continue to create a massive crisis of trust. So a few years ago, along came Bitcoin and blockchain technology. And then we had other blockchains such as Ethereum, and all of a sudden we have smart contracts. Now, a smart contract is not smart, and it's not really a contract either, but it can be thought of more as a highly secure, tamper-proof digital agreement. So the difference between traditional digital agreements and smart contracts is that smart contracts run on this decentralized infrastructure like a blockchain, and it enables us to rethink and change the way in which that we execute and enforce agreements, because the big shift is the contract execution and enforcement is done by this decentralized infrastructure that's got nothing to do with the people or entities in the agreement itself, right? It's this complete separate thing that no one can kind of have influence over and kind of hack or do any kinds of things like that. So why is a smart contract better than a traditional digital agreement? It basically comes down to 5 fundamental things. So the first one is security. The tamper-proof digital agreement, it can't be influenced by a single party because it runs on this decentralized infrastructure, right? It can't be hacked. No one's going to hack your program or your system and kind of change it if it's running on a blockchain. 2, reliable guaranteed execution. So once again, because it's running on this decentralized infrastructure with nodes, usually all around the world or highly decentralized, it's always going to be running 24/7, 365. The blockchain doesn't go down unless there's some kind of worldwide power outage or internet outage or something, right? So there's no like Visa or MasterCard scenario where their payment processor goes down for a few hours and it's like, oh, we can't process payments. It's constantly running, and it's always going to execute your code. 3, transparency. So in a traditional digital agreement, transparency is usually hidden from certain participants for reasons, whereas in a smart contract scenario, the transparency of the agreement and its enforcement is unavoidably built in, right? 4, trust minimization. So we get reduced counterparty risk. Because of the blockchain and decentralized infrastructure, we can kind of interact with each other and participate and kind of do things with each other without having to trust each other as much, because we're trusting on the decentralized infrastructure that is the blockchain and the smart contracts running on it. And 5, efficiency. So all of these traits that I talked about, security, guaranteed execution, transparency, trust minimization, they kind of provide an opportunity to kind of take some of the existing manual processes and kind of automate them and kind of create all kinds of efficiencies. Basically, trust isn't cheap, trust is expensive. So by minimizing trust, there is definitely gains that can be found. So just to reiterate on this section, brand-based guarantees have high counterparty risk with low transparency, but smart contracts, which are math-based guarantees, we have, it's basically the opposite. We have high transparency and low counterparty risk. And, you might think about this and say, well, banks and all these other companies aren't going to want to kind of migrate to something like this where they have less control and all those types of things. But I think history has shown us in the past that generally the better user experience always wins out in the end once it can scale and cost doesn't become a factor. So we've seen countless examples of this in the past, with such as videos moving to streaming services and music moving to streaming services. Software as a service was huge. Companies said back in the day, no, I'm not going to put my data on some network outside of my local network. I'm not going to put it on the internet. But now we see not only does data go on the internet, but the most valuable data goes on places like Salesforce and Xero and places like that. And even back in the day, department stores, they didn't want people doing internet banking. They wanted people going to their stores. And even banks, they didn't want people doing, internet commerce. And banks didn't want people doing internet banking. They wanted people going to ATMs. Once again, the best user experience always wins out in the end. And we've got a couple minutes to answer some questions on smart contracts now. I've got another poll as well.
Harry, is there a way for us to turn on the Q&A feature too? Or we have to like restart? If we got to restart, obviously we don't want to do that.
No, we can't turn on the Q&A, unfortunately.
Okay.
That is for webinars.
Ah, gotcha.
So I see Arlo asks, why are interest yields consistently high in crypto? And yours says no middlemen. So that's definitely true. I also think that there's still a high risk profile in smart contracts. And so the market has kind of priced interest rates as such.
Nice one. Any other questions you can see?
Yeah. Sorry, Zach, did you just answer smart contract is transferable? I don't think you did, right?
No, you can take that one.
So, yes. The really general answer there is going to be yes. So anything that you can code, you can do. And you can code your smart contract to be transferable, right? To either transfer a token or transfer ownership of the smart contract. So yeah, they're definitely transferable. Somebody else also said, since that was a quick one, monthly salary could be turned into smart contracts, right? Yes, 100%. In fact, there's a pretty cool project out there called Superfluid, and they have a streamable token. Like it's a token standard where it actually streams a token to a user that doesn't cost any gas, which is really cool. And yeah, so your monthly smart contract could absolutely, and that's the exactly the type of thing that smart contracts are looking to solve, right? To these cryptographic math-based guarantees. If someone says, "Hey, I'm going to pay you $50 a week," well, that smart contract code will do exactly that. It'll pay you $50 a week.
I saw a question, can smart contracts automatically renew themselves? So once you deploy a smart contract to a blockchain like Ethereum, they just stay there. They exist, they stay in state, and they live there forevermore. And the one limitation is, though, a lot of methods and functions in smart contracts cannot be run automatically on their own. And so that's where we have solutions like Chainlink keepers to help that.
Yeah. How do you make sure a smart contract is bug proof? Yeah, you got to have people audit them. And that's really it. So definitely have a testing framework, and you definitely need audits there.
Is there a chance to reach a mathematical model to get 100% secure smart contract? I think that's almost a philosophical question, but I look into math proofs that say like math can't even prove itself. So I don't think it'll be ever possible to 100% guarantee something is secure.
What are the challenges of creating smart contracts? You'll see as we do this, as we go through this demo. Is there a way to automate the auditing of smart contracts? Yes, there are some tools. One of the really good ones is it's a static analysis tool. It's Slither. You can automate certain parts, but at the end of the day, it depends on what you want your contract to do, and maybe you want your contract to have some crazy exploit. And yeah, so those tools are coming out more and more, but yeah, you still need some human intervention at the time.
Yep. All right. Just quickly, the poll that I shared, or trivia question: who first came up with the concept of smart contracts? So the options were Satoshi, Sergey Nazarov, Nick Szabo, or Vitalik. And the answer to that is Nick Szabo back in the 90s. Okay, I think we're out of time, so we'll have to move on now. Cool. Let's talk about Ethereum and Solidity now. So Ethereum is a permissionless or public blockchain that's open source. You can go and see what the code is for yourself. And basically, it can be thought of as a transaction-based state machine. So basically, it transitions to a new state by reading a series of inputs and forming them into blocks. And it currently uses the proof of work protocol that I was talking about before, that kind of does the kind of cryptographic puzzles to kind of find the correct nonce. But it's in the process of transitioning to what's called proof of stake. And if you want to know more about it, there's lots of information on the internet. Highly recommend going down the rabbit hole if that's your sort of thing. So in terms of the components of Ethereum, we've got nodes, accounts, and confirmed transactions and pending transactions. So I'll just give you a quick idea. So in terms of nodes, I can't remember how many there are, but last time I checked, there were over close to 20,000 maybe all around the world for Ethereum. And there's different node clients as well. So different software that kind of adheres to the Ethereum protocol standard. And the reason for this is for, decentralization purposes. If there's an issue with one client, we want to have different clients to kind of pick up the slack. So we've got accounts as well. So we'll go through more about addresses and accounts in a little bit. And we've got transactions, which obviously transactions sending some ether or crypto to someone, sending a token to someone, or interacting with a smart contract. And we've kind of got pending transactions as well. So it's what's called the mempool. So any transactions that have kind of just been generated and are kind of sitting there unprocessed, they sit in this kind of pool of transactions that miners then take and kind of bundle up into blocks into the blockchain. So the Ethereum virtual machine, let's talk about that. So Ethereum is what's called a Turing complete 256-bit virtual machine. So basically it's an application platform, right? All nodes running the Ethereum client have the virtual machine on them, and they can execute smart contract code. And basically the Ethereum smart contracts are executed in this virtual machine. So we program the logic for these smart contracts via a language such as Solidity. And then these instructions are kind of compiled into what's called EVM bytecode that the EVM can kind of read and process. So Ether is the native cryptocurrency of the Ethereum network. The symbol is ETH, and it's used for transaction fees and computation, such as executing smart contract code. Now, you may have heard of the concept of the token as well. And if you don't know, a token is basically just a representation of any tradable good or service or unit of account. There's a whole lot of use cases for tokens, and generally most of them adhere to what's called the ERC20 token standard for building these types of tokens. But the Chainlink token is actually what's called an ERC677 token, which is the same as an ERC20, but has like a couple of extra features that Chainlink requires. And so when you're kind of sending tokens and doing things with tokens, you don't think of it as kind of something like Ether or a native cryptocurrency. A token is just a smart contract, right? It's just a smart contract that has a whole list of addresses that says who's got what. And when you send a token to another account, the smart contract just updates and said, okay, this person's got this now and this person's got this. So a token is really just a smart contract. So Solidity is the main language used for creating contracts on Ethereum. And it's very similar to using JavaScript or C#. And the commands you create and the contracts you create get compiled and executed in the EVM. And there's a whole bunch of libraries that you can use, and there's some good documentation. And the argument for kind of creating a specific language for this was because compilers aren't generally optimized for storage. Even the simplest C++ program, can be like 4 kilobytes or more. So in a scenario with blockchain and thousands of nodes running the software and all this kind of redundancy going on, we need to kind of be as lean as possible. So Solidity focuses on kind of that problem there, and also it really focuses on security. So a lot of other compilers don't really put a focus on security as much as what is needed for a decentralized ledger. So Solidity's got a high focus on security as well. And Solidity isn't native to just Ethereum. It's used on a whole bunch of other Ethereum virtual machine compatible chains, such as Polygon, Binance Smart Chain, and many others as well. So when you create a Solidity smart contract and you compile it, it basically produces two things, right? It produces the bytecode, which is the EVM low-level instructions that I talked about before that the EVM needs to kind of deploy your contract and execute it. But it also produces what's called an ABI definition. So an application binary interface. And what it is it's basically a string of JSON, as you can see in the example here, that specifies how another program or anything can kind of interact with the smart contract. So it says all of the functions that can be called, what you need to pass to the functions, what they return, all the events and things like that. So that when a contract is deployed on Ethereum and you have other applications, other contracts, anything else that wants to interact with it, the ABI basically allows them to know how they can interact with that contract. So the contract is published to the blockchain after it's compiled by uploading the bytecode, and it's assigned its own specific kind of special address. And to access the contract, you need the ABI definition, as I said before, to know what the inputs and outputs of the contract are. So let's talk about gas payments now. So executing smart contracts isn't always free. Sometimes you need to spend what's called gas. And gas is the internal unit for keeping track of an execution cost. And it's split into two things. We have gas cost and gas price as well. So gas cost is always static depending on what you're doing. So if you do the same thing multiple times with the same inputs, you're going to incur the same gas cost. And you can kind of think of it like driving from one place to another with your car. You're always going to generally use the same amount of gas, give or take. It's the gas price that can actually change those. So this is how much someone is willing to pay for the gas. So how much did you pay for the gas to put in your car when you had to go from point A to point B? So gas is measured and paid for at each contract execution. So every time you interact with a contract, that's where you kind of specify how much gas you want to put, right? So when you're reading data from the blockchain, it's free. You don't have to pay any gas. But when you kind of write and do other kind of operations, that's kind of where you need to specify a gas amount that you want to pay. And it's set by you, the transaction caller, and the lower the price, the more time it could take for a miner to include them in the next block, because the miners would generally prioritize transactions that have a higher fee because they're going to make more money off of it. So because we're running this decentralized, basically virtual machine on thousands of computers all around the world, we can't just have programs running forever, right? So there's what's called a gas limit that's been introduced. And basically it limits the amount of gas that can be used in a transaction to avoid this exact issue where you kind of have functions that are kind of going and never ending. So if the limit is reached, the contract execution will be terminated, and any changes to the contract state will actually revert back to what it was. So an Ethereum block is mined roughly every 15 seconds, give or take. And there's not a transaction limit per block, but there's actually a gas limit. So there's about 15 million worth of gas that can be included in each block. So depending on what's being done in the transactions themselves, usually equates to about 200 transactions per block. So just to reiterate, anything that doesn't change the blockchain, such as reading blockchain data, reading a smart contract, reading someone's account, how much they have in their account, etc., that's free, doesn't cost gas. Anything that changes the blockchain state, anything that writes the smart contracts, sending ether to someone, executing contract logic, etc., that costs gas. So let's talk about what happens when we have Ethereum, when Ethereum has transactions sitting in this unprocessed transaction mempool waiting to be processed. So for any of those who kind of catch a bus to work or have experience catching a bus, we kind of understand that, when there's a fair few people at a bus stop, everyone's kind of lined up, and when the bus driver comes, everyone gets on the bus in an orderly line, and people generally pay the same amount. I know that there's students and pensioners and stuff, but generally we'll say that they pay the same. So you can think of what happens in Ethereum, where the bus is kind of the next block that's waiting to be mined, and the bus driver, he's the miner that decides who's going to get on the bus on the next block, and the people, they're the transactions. So the miner kind of decides which transactions are going to get on. But in Ethereum scenario, it's not a first come, first on the bus and everyone pays the same. The miners will generally look at the mempool and pick the transactions that's going to make them the most money. And this is fine when the amount of transactions in the mempool is kind of less than what a block can usually handle in one block. So, you know, when there's 100 or less transactions sitting there, but when there's more than what can fit in the next block, that's when we kind of start to see these what are called higher gas prices happen, because everyone wants to get onto the next block or on the bus in this scenario, and everyone knows that there's a whole lot of people or transactions waiting to go onto the next block, and they know that the miner is going to pick the people that offer the most transaction fees. So of course, everyone starts offering, you know, 2 times, 3 times, etc., higher transaction fees because they want to make it to that next block. And you as someone who's, you know, initiated a transaction, you can do that as well, or you can kind of leave your transaction fee as like a normal one, but you run the risk of not only not making it into the next block, but then if there's still a high load of transactions sitting to make it into the block after that, then you can also miss out on that block, and then the following one and the following one. And that's generally what happens. So when you see the term of Ethereum, you know, all clogged up and we've got all these high transaction fees, you know, that's what's happening. And that's generally how it works. There are other things and scenarios such as MEV and things like that. But for the purposes of this introductory bootcamp, we'll kind of stick with this analogy. So let's talk about contracts and functions now. So a contract in Solidity, you can kind of think of like a class in a normal object-oriented programming language, and they can hold data and functions. And like I said before, the execution of them is paid with gas. So for those who are familiar with other programming languages, we've got visibility of functions as well. So public and private, pretty much how you'd kind of think it is. Public can be called by anyone, private, accessible in the contract only. We've got these 2 other ones, external, which is kind of like public, but it's more actually designed to be called externally by other contracts and systems only and not internally. And we've got internal, which is kind of where it can be called from within the current contract or any other contracts that derive from it, right? Whereas with private, it's not accessible from derived contracts. Okay. So here we've got a couple of examples of how a function can accept parameters and kind of how you can specify return values. So once again, if you're familiar with other programming languages, it's more of a case of just knowing the syntax here. So in this case, we've got a store function. We've called it store. It takes in one parameter called num, and it's defined as an unsigned integer in this case. And in this case, this is a public function, so anyone can call it. And in this case, all the function does is it assigns a variable called number to the value of this num parameter here. And so this is an example of a function with no return value, but with a parameter, an input parameter. And this example here is another function, but this time we don't have an input parameter, but we have a return value instead. So this function is called retrieve. There's nothing in the brackets there, so there's no input parameters. This one is a public function as well, so anyone can call it. We also specify view here. This is a special kind of reserved word or modifier that you can say that basically says to the EVM, to the compiler, hey, I'm not changing the state here. Don't charge the person any gas for this. I'm just like reading data. So that's kind of what that means. And in this case, we're returning an unsigned integer 256 value. And in this case, we're just returning the number variable here. So data types in Solidity, very similar to other programming languages. We've got integers and unsigned integers, Boolean, true or false. We've got strings, bytes of data, up to 32 bytes of string data, Ethereum addresses, which are 40-character hex strings encoded with a checksum. So there's an example there. And we've got what we call enumerated types, which is basically just a user-defined type. So in the example there, we've kind of called it direction. We've said it can be up, down, left, or right. So let's talk about arrays quickly. So very similar to other programming languages, arrays can be a fixed size or they can be dynamic. And they've got members that you can kind of use and call, such as length to find the number of elements in the array, and push, where you can kind of add elements to the array there. So there's a couple of examples of fixed size and dynamic arrays there. In Wednesday's session, we'll do a couple of little exercises in Solidity that deal with arrays. So we've got what's called maps as well. So they're basically a key value pair. So a good analogy is, imagine you've got mobile phone numbers in your phone, and you've got a phone book, so that if you ever need to call someone, you don't need to look through a whole list of mobile phone numbers. You don't need to know the number off by heart. You can just type in their name and it kind of comes up with a number. So same kind of scenario there. We have a key and a value, and they're used quite extensively actually. And in Wednesday's session, we'll go through an exercise that kind of deals with maps as well. And finally, we've got what are called structs. So a struct is actually a collective of primitive types in Solidity, where you can kind of take some of these other data types and put them together into like this one kind of object. There are some restrictions that are listed there, but generally it's pretty basic. You can see an example there. We've created one called account. It's got an address and an unsigned integer in it. You can kind of create it, and then you can kind of set the values as you wish after. Cool. Okay. I'll just launch another quiz for you guys while I get the demo ready. Can we please post the exercise into the chat in YouTube and Zoom? And we'll kind of maybe try and do this first one together. Also, we've got time for a couple of questions if any of the helpers want to answer any.
So I asked a question like how would the state scope? I think in Solidity you can use public and internal, external, and a private keywords to set up the state scope, I think.
It's a question. When I create a smart contract, should I create a token to go along with this functionality, or could I just use Eve? And that's really a design-specific question. Tokens have a lot of really cool use cases that can improve your smart contract, but requires a lot of thought. Typically, when you're trying to coordinate a lot of people together, a token is super useful, but you don't have to use one.
So I just want to do a quick comment on something somebody said. They said, hey, like, I feel like everyone here is so smart. What's going on? Don't let imposter syndrome slow you down. So that's just something a lot of people new to the space kind of get into. They come in, they see a whole bunch of people who kind of who've been in the space a little bit, asking questions. They feel a little bit flustered. Don't worry about that. everyone who's come into the space had to go through this kind of like, oh, like what's going on here. So just don't be afraid to ask questions. You're definitely welcome here. You're in the right place. There's a lot of people who are kind of shy and won't ask questions, but yeah, please ask a million questions everywhere. That's how we're going to learn, and welcome to the space. Really excited to have you guys here. So just
Also
wanted to say that do not feel imposter syndrome. You will, but don't worry about it. Do not worry about it.
Also to add on to that, remember, like 98% of the world is also still learning all of this stuff. So you're not alone for sure.
Yeah, spot on. There's what do we say at the beginning? 50,000 active Solidity developers on the planet. That's like a drop in the bucket comparatively. And onto a technical question. I don't think we answered this one yet. Difference between external and public. So external just means it can't be called by that same internal smart contract. So public means, yeah, anybody, free range, whoever. External means it's got to be called outside of that smart contract. So you can kind of think of it as it can't call itself.
What's the difference between a coin and a token? Those are kind of used interchangeably in the blockchain space. Typically, I've seen some people say like, oh, if it's got its own blockchain, it's a coin or a cryptocurrency. And if it's built on a smart contract, it's a token. But some people just use them interchangeably.
Yeah, on the topic of view functions that are free, not free, there seems to be a little bit of confusion there. So if you want to call a read function, a view function, excuse me, off chain, you can just do it for free. If you call a view function inside of a state changing transaction, it will cause gas. I know that that's a little confusing, but you'll see once we get in here, kind of what that means. Like if you were to call a view function inside of another function that isn't a view function, then it would cost gas. But if you just call a view function purely as a view function, it won't cost gas. Hopefully that is helpful there.
Yep. All right, let's move on before we fall too far behind.
Yes, welcome imposters. Feel free to take off your imposter masks. You are welcome here. I saw a couple other people respond to that. So you are all 100% welcome. Welcome, welcome, welcome.
Awesome. The poll that I just launched, who invented Solidity? Gavin Wood, Vitalik Buterin, Nick Szabo, or Satoshi Nakamoto? The answer to that is Gavin Wood. Now, hopefully you guys have the link to the first exercise. I was thinking maybe we could try to do it together. So let's just try and we'll see how it goes. And hopefully we have enough time for everyone. Can we post it in the chat again in Zoom? I think it was lost. So if you've got two monitors, definitely throw Remix on one and the meeting here on another, or the exercise on another. Is everyone able to load Remix properly? Yeah, cool. All right, if it doesn't work, maybe just try reload. So the first exercise, we're going to create just a simple smart contract that that basically stores a variable and kind of has a function to modify the state. So the source is in the exercise, but let's try and do it together if we can. So let me know if you guys can see that or if it's too small. But essentially, what you need to do first is create a workspace if you haven't already, which basically is just a collection of stuff that you want to create. And then in your contracts folder, we're going to create a new contract by pressing on that button there, and we're going to call it whatever it says in the exercise, my first contract. So once you guys have that open, I'll give you guys just 20 seconds to try and do that, and then we'll move on. All right. Have some of us got a new contract ready to start coding? Yep. All right, cool. So the first thing we're going to do is we're going to specify what's called a pragma statement. And what this basically specifies is which version of Solidity, of the Solidity compiler, or which versions we want basically our smart contract able to be compiled with. And when we get to the compiling stage soon, you'll see there's so many different versions of the Solidity compiler with all these kind of upgrades and fixes and things that some contracts you only want compiled on certain versions. So in this case, we're saying we want it to be compiled with at least 0.6.7. And I think by adding this little up arrow thing here, I don't know what that's called. I think it basically says that it can actually go up to the next major version, which is probably 0.7 or something, but not higher. So that's the very first thing we're saying in our smart contract here. So let's all put that in. You can kind of type it in manually or grab it from the chat. Oh, yeah, there you go. It's called a carrot. Learn something new every day. So let's all throw that into our contract as the very first thing. Gives you good eyesight and it compiles your smart contracts better.
Harry, can you zoom in just a hair?
Sure.
Maybe 1 or 2.
How's that?
A little bit more. Yeah, nice and big. Thank you.
Sweet. All right. So once we have our Solidity version specified, we're going to create a new contract here. So we go contract, my first contract, and just like how you do with a class, in other languages, we're going to put it in the curly brackets, and that's kind of how we define our class. So let's all go and do that now. I'll give you guys 10 seconds or so. So once we've created our class, we're going to want to put all of our stuff that we want in our smart contract. Once we've created the contract, we're going to want to put all of our stuff we want in this contract here. So all of our functions, all of our variables and things like that. So hopefully you guys have created that contract now. So the next thing that we're going to create is we're going to create a new variable, and we're going to call it number. So that's the syntax. So this is an unsigned integer, and that's kind of how we create the variable there. So if everyone can go and do that one next. So we're saying in our contract, we want to create this new variable. It's an unsigned integer, and we want to call it number. So hopefully you guys have been able to do that. So the next thing that we're going to do is we're going to create a function, right? We want a function to basically return, actually we'll do the setter first, but we want to create a function to modify this number variable in our smart contract. We want to basically create a function that says, hey, I want to change what's in this variable called number. So the syntax for that is we go function change number. And in this case, it takes in one input variable. So it's a uint, and we're going to call it num. The general, what's the word? The general thing that people do is they put like an underscore for these input parameters. So we're going to specify that this is a public function. So anyone can call it, not just us. And once again, we're going to put our curly brackets, and there we go. There's our function that's been created now. So I'll give everyone a few seconds to create that as well. Yeah, for those who ask in the chat, UINT 256 is by default. So you can also do that, or you can not.
Real quick, I saw someone ask, why do you have different bit sizes for variables? And if you know that you're going to have a limited range for a UINT, for example, and you don't want to use 256, you can save your users gas costs by optimizing the size of the variables.
Also got a question for somebody saying their compiler is saying it's missing the SPDX license identifier. Don't worry about that for now. We'll get into that later. But yeah, that's just don't worry about that. If on your compiler tab it has like yellow things, those are just warnings. You don't have to worry about them. If it's red, that's an issue.
Yeah. So in our function, like I said, we just want to change the state of our number parameter. So we're just going to say number equals, num. So very simple. We have a change number function. It takes a parameter and we're changing the state of our contract. We're updating the number variable to be what's passed into the function. So that's our first function. So I'll let you guys just get that one all sorted. So yeah, for those who are from Java and other languages, you can kind of think of this as kind of like a setter function for that number variable. So the next function we're going to create is we want to create one that just returns the value of that number variable, or a getter function, if you will. So we're going to call it getNumber. This time it doesn't take any inputs here. So we've got empty brackets because we don't need to specify anything. We just want to return what's currently stored in the contract for this variable. Once again, it's a public function. Anyone can call it. It's a view function. We're not modifying the state of the blockchain here. And in this case, we are specifying a return type because we're returning something here. And we've got our function there. And all we're doing in it now is we're just returning the number variable. So I'll let you guys catch up and put that in. And then we'll move on in a little bit to compiling and deploying and stuff like that.
While you guys are doing that, saw a couple questions here. Someone said, hey, why is the G lowercase and the N uppercase? This is just by convention. It's called camel case. If you want to look it up, it's just a way to write the names. You have the function first letter lowercase, and then like any word that you would do next, like uppercase. So change number, since it's two words, change the number, change the lowercase, and then the N in number is uppercase. And yeah, it's really for readability, so that it's not just like one giant garble.
Yeah. Okay. So hopefully now you've created your smart contract. So the next thing that we're going to do is we're going to compile it. So on these little tabs on the left-hand side, the second one here with a little S kind of thing is the Solidity compiler tab. So you click on that one and you can kind of leave everything as default, I think, and you should be able to just hit the compile button. And you might get this warning down here, but like Patrick said, you can kind of just ignore it for now. So what you'll get basically when you compile it is you'll get, like I discussed earlier, you're going to get the bytecode and the ABI, and you can actually kind of take them and let me see if I can paste this. Well, too much. So as you can see, that's the ABI for our smart contract here. So we've got the get number function. We've got the change number function. Here are the inputs for that. Here are the outputs for that function. So there's kind of the ABI as I described earlier. So our smart contract is now compiled. So the next step is we want to deploy it, right? So the tab underneath the one we're just in is the deploy and run transactions tab. So that's the next one that you're going to want to go to. So everyone, if you haven't compiled your contract, go to the Solidity compiler, hit the compile button, make sure you've got no kind of red errors there. If you've typed everything as per the exercise, you should be good to go. If you get an error, just double check your code against the code in the exercise. And then go to the deploy and run transactions tab next. For those who are asking where to view the ABI again, back on the compiler tab, once you compile, you get kind of this little ABI and bytecode button come up, and you can kind of just click it to copy it to the clipboard here. So in our deploy and run transactions tab, we actually have to specify what environment we want to deploy the smart contract to. So before we go to deploying it on an actual network, we're going to deploy it on what's called the JavaScript VM. So Remix has this cool library that kind of simulates running a blockchain in your browser. So you can kind of deploy smart contracts to, and you can kind of interact with them and do all types of things. And it's all really fast and easy to use. So if you're just doing basic Solidity things like this, it actually speeds up your development really well. So let's stick with a JavaScript VM first. So you kind of pick a JavaScript VM, Berlin or London, doesn't really matter. Make sure your contract selected is your contract that you've created just now and compiled. And let's press the orange deploy button. So I'll just give you guys a few seconds to do that. We'll get to using injected Web3 for those who ask. For now, we're going to work on a local blockchain in your browser, basically. So once that's deployed, in your deployed contract section here on your bottom right, and hopefully you guys can see, you can see it kind of down here, and you can kind of expand by pressing the little arrow. And you can kind of see we've got some buttons here. So we've got an orange change number button, and we've got a blue get number button. So Remix will kind of take the ABI and look at your contract and kind of generate this information so that you can kind of have this kind of cool little graphical user interface way to interact with your smart contract. So blue buttons are kind of buttons that you can kind of call and don't change the state of the blockchain and don't require gas, and orange ones are ones that kind of require you to generate and sign a transaction that will kind of cost gas. Okay, for those who are asking about the last couple of steps post compilation, once you've compiled, click on the little Ethereum logo tab on the left here and press the orange deploy button. That's kind of where we're at now. And yeah, once we finish this first exercise, we'll have a 2-minute break for those who need to duck away quickly. So once that's deployed, we can actually interact with it straight away. So you can press the blue get number button, and you can kind of see we get a result of 0. So this is because there's nothing in the number variable yet, but we can actually put in a value into the change number function input there and press change number. And you can kind of see in the log down here, we kind of get a successful transaction. And if we then hit the get number function now, we get the figure that we put in. So there's a simple example of deploying and executing a contract on a local JavaScript virtual machine as opposed to a real Ethereum blockchain. and we just simply modified the state of our smart contract and then called a function to kind of return the value there. So I'll give you guys a few seconds to just kind of test that out and play around with it, and then we'll move on.
Hey, got a question here while you guys are doing this. How to define the default value. So Solidity actually defaults numbers and variables to the none, whatever none is. And for a number, it's going to be 0. So when you do uint number, it's defaulted to 0. But oftentimes you'll want to default it in a constructor, which we're not going to get into. But yeah, for now, just know it automatically defaults to 0.
Yep. Okay, so hopefully you guys have had a bit of a play around with that. So what we're going to do now is we're going to take our same compiled contract and we're going to change the environment to injected Web3. So this basically means we're going to now use our MetaMask wallet. And hopefully you guys have set yours up. And what we're going to do is we're going to deploy our smart contract to the Ethereum Kovan testnet. So it's a copy of the mainnet. There's no real value in the Ether and tokens and things like that, but it's used for kind of testing purposes like this. And when you change to injected Web3, you may get a pop-up from MetaMask saying to kind of connect your wallet and things like that. So if you do get that, just hit accept. But once you've done that, you should see you've still got your contract selected here. And what we're going to do is we're going to once again hit the orange deploy button. And this time we're going to get a pop-up notification from MetaMask saying, hey, I heard you want to deploy your smart contract to the Kovan test network. Can you please approve this transaction? And it gives us a kind of gas fee. We could specify the gas price and the limit. We can kind of leave them as default values. And just hit confirm. So you'll need to have ETH in your MetaMask account. So if you haven't got ETH, definitely go to the faucet in the setup instructions and try and get some. And once that's done, we have a deployed contract here, and you can kind of do the same things that we kind of just did. The difference is when you call the change number function, once again, you're going to get a MetaMask notification saying, hey, you want to interact with this smart contract on Kovan, here's what you kind of need to specify. So you just leave everything as default and just hit confirm. So the difference between this and the browser virtual machine is that we have to wait for blocks to be mined and things like that. So it's not as quick, but it's on a real Ethereum blockchain that's kind of like a copy of the mainnet one. So as you can see there, I was able to successfully change the number variable, and we kind of get it coming up there. So I'll leave you guys for a minute or two now to play around with that. Once you've done that, that is the end of the first exercise. So we'll take a 2-minute break and then we'll continue. So yeah, have a play. And if you have any questions, feel free to ask.
Deployment might take maybe even up to a minute or two. Like what Harry was saying, we have to wait for our block, wait for our transaction to actually get included in one of these blocks.
I have a question.
Shoot.
How do you decide what the gas limit is? So when you create a deploy a contract, it comes with a MetaMask gas limit and then price. How do you decide what is a good gas price or a good gas limit? That'd be a stupid question here.
Oh, that's a great question. So MetaMask kind of has an algorithm in the background that helps you pick that based on what it sees other people putting in and what has been put in the past. But you can actually, when you're making a transaction, click, I think, on advanced settings, and you can pick the exact gas limit you want to pay for that transaction, and it's kind of up to you. So maybe you think the MetaMask algo isn't accurately saying what a fast gas price will be, then you can make it yourself.
Okay. Would this also be just better? You'd learn this over time in terms of what the correct gas limit and price would be. Is it something? Yeah.
Yeah. I mean, MetaMask is usually pretty good. You know, if you click on their fast speed, it'll usually get in pretty fast. It's just when the blockchain is going crazy and everyone's trying to transact at once, sometimes that algo can lag, and you're going to want to kind of set it yourself.
Okay, sure. Thank you.
No problem.
I had a question on compiler versions. I was wondering why we were using 0.6 rather than the latest, and if there's any significance in choosing specific compiler versions.
So generally, you want to pick a compiler version that, if you're making a new contract, it's general practice to go with the best, the latest stable release of Solidity. But otherwise, you may have dependencies in your contract that require an older version, and that kind of forces you to go down. In general, you know, Solidity improves with each version. They add cool new features that they make development better. So that's why you kind of want to go with the latest. Hey,
if
Harry.
you guys have, yep, sorry, Zach.
I was just going to say, I'm seeing several questions on how to connect Remix to MetaMask, if you want to quickly show people.
Yeah, sure. So if you click on your MetaMask little fox thing in your browser here, you should see, or if you're not connected, you won't, but in the top corner here, there should be a connect button if you're not connected. So mine's green and it says connected because I'm kind of connected to Remix. But if you're not, try and press that connect button and it should kind of get you to where you need to be. If you've finished, sorry, I was just going to say, for those who have finished the exercise now, there's a couple bonus things you can try and do over the next couple minutes. Otherwise, if anyone wants to take a quick break, we can do that. We'll probably have about a 3 to 5 minute break now, but hopefully you guys have had a good idea of kind of deploying a smart contract to a local VM to Kovan and kind of playing around with it by now.
I have a question to the connection. It says on the MetaMask that I need to find a button in the Remix environment and press connect.
In Remix?
I guess so.
Okay. Usually when you select Web3, it should kind of do what it needs to do. Are you not getting that? Is it? Has anyone else been able to successfully connect MetaMask?
When I just injected Web3 or changed the option and just tried deploying with the orange button, it asked me to connect it and then pay the gas. So
yeah,
should try deploying with the correct option there.
Yeah, the environment needs to be injected Web3.
Are you using the same browser where MetaMask is installed?
Yes. And yeah, when I pick up the injected Web3,
and sorry, just quickly, in your MetaMask here, make sure that the network you have is the Kovan network selected as well. That could be the issue too. Yeah, for those who can't stay for the full session, we will be releasing videos on demand, definitely. So we'll take a 3 to 5 minute break for people to complete if they haven't completed, and then we'll move on to the next section.
Harry, I have a question for you.
Sure.
So I successfully deployed and I set a number. So I made it 777, like your example. So MetaMask popped up and I confirmed the transaction. It gave me a address on Etherscan where I can check the transaction. So I go there and I'm looking for that number 777 that I input. You know, was it written to the blockchain somewhere? Can I see it on Etherscan, the input that I gave?
Yeah, you can see it, but it's kind of in hex and stuff, so it's not as readable as you probably think it is. So that's a good point, actually. In the exercises, we basically deployed the contracts, and you can kind of press this button to copy the address, and you can paste it in coven.etherscan.io, and you can kind of see all of the transactions that you kind of interacted with your smart contract.
Okay, and where is it hiding that number that we just told? Oh, I see it here. No, that's not it.
Yeah, so here's the input data that we specified. So you'd have to kind of convert that to kind of get your 777.
Okay, so that's hex. I convert to decimal and it should be 777. All right.
If anyone still has issues with deploying and executing before we come back from the break, feel free to put your hand up in Zoom if you're in the Zoom session, and one of our helpers will kind of help you out privately.
Hey guys, I'm jumping around on the YouTube and on the Zoom to help people out here. Keep asking questions. Like what we said before, you guys are doing great. And then I just wanted to double down on something. For those of you who are brand new to smart contracts, maybe some of you are even brand new to development in general, brand new to programming, and we're able to successfully deploy one of these contracts to a testnet or even just to the JavaScript VM, you know, already give yourself a huge pat on the back. You just deployed your first smart contract. So congratulations, nice work there. Like, you should be really proud of yourself, even just getting this far, right? Because now you already know like an interface to deploy your own smart contracts. So, you know, give yourself a huge round of applause. Again, now if you're like, imposter syndrome, you can pull it off completely now because you are a smart contract engineer at this point because you have deployed a smart contract with code that you wrote. So huge congrats there. Nice work, guys.
Well done.
Yeah, and yes, for those of you pointing it out, there is more to it, but you've taken that first step. So nice work.
Got a quick question.
Yeah, can you raise your hand? So that
Sorry.
Yeah, no worries. Sorry, we're trying to get to everybody here. Yep, and like we said, we're coming around to people with hands up, so just trying to get to everybody here. Nice work, everybody. And for those of you, that are done, like Harry said, go take a pee break, go get some food or something.
Yep. Unfortunately, we're a little bit behind schedule, so we're going to continue in 2 to 3 minutes, and hopefully you can catch up on the next exercise if you need to catch up. if you have your hand up, check your direct messages in Zoom to see if you've got a message from one of our helpers to join a private room.
I have one more question, if anyone's willing to answer.
Sure.
Say if more my knowledge comes from Python, for example, but this is more JavaScript based in terms of like the code. Is it a hindrance or is it just a different language? I don't know. It's just a question I have. I don't know.
Is what a hindrance? Sorry.
Just knowing, not really knowing JavaScript, but knowing like say Python, for example, not even to a high level, but just to a basic understanding. Or is it?
No, I don't think it's a hindrance at all. Yeah, Solidity does have similarities to JavaScript, but it's not like it's some crazy different language. It's more of a case of just figuring out the syntax. If you know a language, a high level language like Python, it's not a long stretch to kind of learn the nuances and syntax of Solidity at all.
Okay, cool. No worries.
Hello, Harry.
And everybody that is not talking, please mute. Sorry.
Yep. Can you guys hear me okay now? Yep, thanks.
Sound lovely.
All right, so let's talk about the Oracle problem and Chainlink now. So, sorry, 1 second. So now that we know why smart contracts are so awesome compared to traditional digital agreements, let's talk about their biggest limitation. So smart contracts are not able to connect to external data or any off-chain resource on their own. Now, sorry, I've just got a small presentation issue. I'm just going to stop sharing my screen for a minute to try and fix it, if you just bear with me. Okay, should be good to go now. So why can't a smart contract make an API call? And the answer to this is because the blockchain is deterministic and everything needs to be able to be validated by all of the nodes on the chain. So if making an API call is part of this kind of execution, then the blockchain can lose its determinism, right? Because you might have some nodes calling an API and getting one result, and some nodes calling it and getting another, and then we kind of lose that determinism. So this is defined as a smart contract connectivity problem, not being able to connect to external data, systems, and events. And it limits smart contract functionality only to be things that can be done from within a blockchain, such as moving tokens around and performing payments in the native asset of the blockchain. So to interact with the outside world, we need what's called an oracle. So an oracle is any device that interacts with the off-chain world to provide data or connectivity to smart contracts. And they report the result of that data or computation on-chain so that the blockchain can stay deterministic. But using a single centralized oracle actually creates a central point of failure for a smart contract and compromises the overall security of your smart contract, because you've got this highly secure blockchain running this decentralized infrastructure, but you're triggering your smart contract on there from this single kind of node or computer running somewhere. And the end-to-end security of an overall system is no better than the weakest link. And in this case, it's the oracle, because it's just a single system compared to this decentralized kind of blockchain that we have. And so now we kind of go from having this really cool way that we can actually get data into our smart contracts, but it's kind of not that secure because of the way that it's triggered. So the next question is kind of, how can we get around this? And the answer to this, a decentralized Oracle network. So Chainlink is designed to be a modular, decentralized Oracle network for getting secure and reliable data on-chain and for triggering external computation. So we bring this data in a decentralized way. And by doing this, we solve this problem by extending the decentralization of and trust minimization of the blockchain out to the data source and data delivery layer. And what this achieves is allowing contracts to take any input from the real world and add it on-chain, as well as any output from the blockchain and kind of send it to the real world, but to do it in a decentralized way. And this end-to-end connectivity and reliability and security is actually the real value proposition of smart contracts. Being able to do all of the digital agreements that we do today, but to do them in a better, more secure, more tamper-proof, automated and highly efficient way. So to try to wrap your head around it, here's a simple example where we've got a number of Chainlink nodes all getting price data from various places, as you can see, with the different kind of price values there. And they're all aggregating the data into a single result that's being posted onto a smart contract. And going back to the point about centralized oracles, we can see that not one node in this kind of diagram here can directly influence the final result. So by combining the on-chain smart contract code with these off-chain resources and services that oracles provide, you have what we've defined as hybrid smart contracts. So these are smart contracts that rely on existing on-chain code and combine it with critical off-chain computations and services. So traditionally, smart contracts are thought of as just on-chain code, but now we're actually redefining what they are. So it's now the on-chain code and the off-chain resources as well. So you can kind of think of them as kind of supercharged versions of smart contracts. And we're already starting to see them redefine what our industry is about. And they'll continue to go on and define how many traditional digital agreements are done today. So Chainlink, as a decentralized Oracle network, it's also blockchain agnostic. So we're not just on Ethereum. Chainlink is on Polygon, Binance Smart Chain, XDAI, and many more to come. Now, any questions before we move on? We got maybe 1 minute for questions.
Yeah, I see Lauren is having trouble connecting. Again, make sure if you're having trouble connecting your MetaMask, make sure it's set to injected Web3 on Remix. The MetaMask itself is connected to shows connected to the website. And if it's still not connecting, make sure to try refreshing the web page and then come back in and it should work.
For those of you who jumped ahead, went to the price feeds, I did just update one of the examples. And yeah, if you see it anywhere else, just let me know. Updated that import thing that was going awry.
Great, thanks, Patrick. All right, let's move on. So going back before to traditional digital agreements I described before and kind of this crisis of trust, when it comes to financial services, people are slowly going to want to seek alternatives, and blockchain and smart contracts are kind of a perfect solution or alternative for this. So DeFi or decentralized finance is defined as all these traditional financial products that are available today, such as lending, yield, the ability to gain exposure and protection from events and risks and derivatives and things like that. But we're putting them on blockchains. We're putting them on smart contracts running on blockchains so that people can kind of perform and do all of these things, but in a decentralized way without the kind of middlemen. And what this does is it provides three things. It gives greater transparency, better yield in many cases, and most importantly, also a high level of control over your assets. You have direct control over them. And we've got some great examples of this. We've got decentralized exchanges, lending and borrowing. We've got Aave, which is a great example of lending and borrowing. Synthetics is a great derivatives platform, and there's many more as well. So DeFi is currently the biggest or most popular use case of using a decentralized Oracle network such as Chainlink. And it's a great example of what we talked about earlier when we discussed hybrid smart contracts. Now, for these smart contracts to operate effectively in DeFi, they need to know price data. They need to know what the price of Bitcoin, what the price of gold, what the US dollar to euro conversion rate is, etc. So to kind of get the industry started with DeFi, Chainlink's gone ahead and created what are called reference contracts, where they take some of the best node operators in the business and combine their skills and experience to kind of create these reference contracts. So these are decentralized on-chain reference points that can be thought of as a source of truth and a trusted aggregated result for price data. So you can say, all right, this is the price of Ethereum right now across the whole market. There's all these nodes that contribute to kind of saying what the price is, and they take data from all of these data sources as well. So the reason for having such highly secure and tamper-proof data for DeFi is because of DeFi exploits. We see DeFi exploits all the time. Projects literally lose millions of dollars due to using centralized oracles or not having enough market coverage in their kind of oracle design. And yeah, if crypto's taught us one thing, if there's a protocol that's open to being exploited and someone can profit from exploiting the protocol, then it's going to be exploited eventually. So you can head to data.chain.link to see some of the available feeds. There's a whole lot there, and we're constantly adding more every day. And yeah, that's it. Let's move on to the demo now, actually. So this one's not going to be done line by line together. We'll actually throw it to you guys, but I'll give you a quick demo. So here is a contract already completed. So it's very similar to what you've seen before. We're specifying our Solidity version here. In this case, we're importing a library. So in this case, it's the aggregator v3 interface library. And for now, we're just importing it directly off GitHub. You can directly go to that URL and kind of see the code if you want. Or not, I'll fix that after. But
Harry, yeah, we literally just recently updated this. You'll have to do the at syntax. Yeah, because we moved the EVM contracts just to contracts.
Yep, got it. I'll fix that. So let me just shut that. So we've created a variable here called price feed, and it's kind of this aggregator v3 interface type. And after that, I'm just going to fix this up quickly. That should be better. Yep. So these are some comments here. This is how you kind of comment in Solidity. Multi-line comments or single-line comments is just // If you're new to development, a comment is just some lines that the compiler ignores, and it's just there for kind of humans to read. And you can see it's kind of this funky yellow color here. So we've got what's called a constructor in our smart contract here. So we've got a smart contract called price consumer v3. The constructor is kind of like a function that just always runs when the contract first kind of gets deployed. And in this case, we're basically setting the value of this price feed variable to, we're calling the aggregator v3 interface here, and we're kind of passing in an address here. And what this address is it's an address of the ETH USD price feed reference contract. So if you go to docs.chain.link, which is a Chainlink docs, and you go to using price feeds, Ethereum price feeds, you can kind of see all of the contract addresses here. So you're going to want to go to the Coven network, which is further down, and you can kind of take the address from here. So we're just specifying to say, hey, we want to use the ETH USD price feed in this scenario. And then we've got another function called get latest price. And all this really does is it basically returns a bunch of data from the price feed contract. And in this case, all we're interested in is this kind of price that's returned. So we're grabbing all of this and we're saying return the current price in the price feed contract.
Hey, Harry, sorry to interrupt. Can you quickly just say what does the aggregator v3 interface function does?
Patrick, did you want to take this one?
Sorry, I was answering another question. What was the question?
What does the aggregator, just in summary, what does the aggregator v3 interface do?
Yeah, so without getting too deep into it, so it's an interface for interacting with the aggregator contract. So you'll learn about interfaces a little bit later on. Don't worry about that too much. But the aggregator v3 contract is just a way to aggregate pricing data. So when you hit that get latest price function, you're actually calling that read function there that's pulling the data from that contract. So you're reading the pricing data from the aggregator contract. The aggregator contract is actually aggregating a ton of different Chainlink nodes and different pricing APIs data to arrive at a reference point of truth. Does that answer your question, or are you still a little confused?
That's great. Thank you.
Okay. Good question.
Great question. So once we're done, like we did earlier, we compile our contract. In this case, we're deploying it to the injected Web3. We want to deploy it to Coven because we're interacting with Chainlink now. Chainlink doesn't know about our local Ethereum EVM running in your browser, so we need to use the Coven network here. When you deploy your contract, make sure the contract drop down here is your price consumer contract as well. And when you hit deploy, you'll get the MetaMask pop up again. And you wait a little bit. And like before, you get your deployed contract. In this case, we've just got the get latest price function here. And as you can see, we get a value return. So what this value is we actually times the result by, I think, 10 to the 18 or whatever it is, so that we kind of we kind of don't have to deal with the precision issues that Solidity has. So Solidity can't handle decimal numbers, it can't do floating point numbers. So Because you might want to do some arithmetic or things like this with these results, we kind of pad it out for you so you kind of get that big result and avoid those issues. So that's about it for the demo. We've shown how to deploy a contract that uses a Chainlink price feed and how to kind of interact with it and kind of get the latest price. Have a bit of a play with the exercise, and we'll kind of continue in a little bit. If you have any questions and you're in the Zoom session, be sure to put your hand up and we'll try and help you out too.
I'm seeing a few questions on the import there. Someone said, hey, like, isn't there like an add thing or something like that? So if you look into the doc, it should be there. Can somebody actually just confirm that they see, like if they hit refresh, that they see the updated import in the doc? We are using the @ however, somebody also posted a URL without the @ that should also work fine. Can you reshare the link to the doc? Yeah, it's there. Okay, cool. So some people are saying it's there.
Yep, it's there.
Cool. And yeah, relink to the doc. Yeah, let's grab that.
So no floats, you said, in Solidity? No decimal numbers?
No floats, no decimals.
Some people are asking about how the @ symbol and how the @ works. I hate to say it, but I would say don't worry about that for now. Basically, it's pulling from NPM, the NPM packages, the NPM repos. If you're unfamiliar with that, that's a package manager for JavaScript. But you can kind of think of it as it's just pulling from GitHub for now. So just think of it like that.
Does the aggregator use gas? To read prices from the aggregator, it does not cost any gas. To SL, he's having trouble. Does not work with the ad address for me. You see on Harry's screen under contract on the left, he has it pointed to price consumer v3. Make sure you're pointing that list to that contract.
We're going to continue, guys, in 5 minutes. So hopefully that's enough for you guys to finish off this exercise.
An interesting point a couple people said, they said, hey, if we do an import and we use that @ and we use like the repo, like the NPM repo that I was just talking about, isn't that a centralized point? That's a great point, and the answer is yes. And that's actually why what a lot of projects will do is they'll copy paste the imports. So they'll go to the site, they'll copy the code, they'll paste it into their own code. It's a lot easier for us for now just to use it. But yeah, if you're really concerned about that, you can just go to where the code actually is, just copy paste it into your application.
Hello. Can you give us the link of this playlist?
sure. I'll paste it in both chats. It's on Spotify.
And again, if you have your hands up and you're looking for support, make sure you're checking your direct messages in the chat. People should be sending out Google Meet invites.
Quick question: does the gas price matter when submitting transactions on the testnet? Does it just have to be non-zero, or does it?
It doesn't matter as much. I guess the testnet can become crowded or clogged up with transactions as well. I know there's definitely less nodes running and things like that. But generally, I've found from personal experience, whatever the kind of suggestion for a normal gas price is usually sufficient for Kovan. Two more minutes, guys, and we're all going to move on.
Hi, I have a question. Can you please explain what is Oracle in Chainlink?
Sorry, was the question what is Oracle and Chainlink?
Yeah.
Yeah, well, we kind of went through that before on the slides on Chainlink, but basically you'll get a copy of the slides after, but basically Chainlink is a decentralized Oracle network. So it's a network of oracles, which are computers to bring in off-chain data into blockchains and to do off-chain computation for blockchains. But yeah, definitely reference the slides after the bootcamp if you kind of miss those sections that we went through before.
Okay, thanks.
Again, guys, if you're raising your hand and need some support, we're DMing in the chat to you guys to join a Google Meet. It's way easier to help over Google Meet, so we can help troubleshoot through whatever problems you're having. So definitely keep an eye out on that chat.
Yeah, DMs in the chat come up with like a red private text or something next to them, so they stand out against the normal chat in Zoom.
What are some typical uses for these price feeds in smart contracts?
Yeah, so DeFi, decentralized finance products and protocols are definitely one of the biggest use cases. So things like lending and borrowing on the blockchain, derivatives and things like that, some really popular use cases of using price feeds. All right, I think we need to move on now. So if you're still going, hopefully you can catch up when we do the next exercise, which is very soon.
1 second.
Sure. Okay, so let's just go over now how Chainlink can access any API. So Chainlink is more than just price feeds. Chainlink provides the ability to connect to any API as well. So it can be used to integrate to any API, whether it's a web API, an enterprise system, a database, IoT sensor, you name it, Chainlink can connect to it. So the way in which it can kind of connect to kind of any kind of external API is via the use of what are called adapters. So there are what are called core adapters and external adapters. And with core adapters, you can kind of do basic API requests doing HTTP GET, HTTP POST, and things like that. And if you need to do anything custom, connecting to databases, reading files and things like that, you can create what are called external adapters. And an external adapter is kind of like just a standardized API with a structured input and output. And a Chainlink node uses it to kind of connect to kind of the API that you want and then kind of do the processing that you want and then kind of return a structured set of data. And we don't have much time in this bootcamp to go through them, but there's some great reference material on our blog, on our docs, if you want to look into creating external adapters and using external adapters. So I highly recommend searching for external adapters on our docs blog and even our YouTube channel if you want to kind of go down that rabbit path. So yeah, there's a whole bunch of what are called jobs that we can kind of use to kind of make these API requests. And there's a website here called market.link where you as a community member, if you're running a Chainlink node and you create jobs, you can kind of list them there and then people can kind of find them and consume them and kind of use them as well. Maybe for another future bootcamp, we can go into this in more detail. But for now, just so that you're aware, we have this kind of market where you can kind of go for and look for jobs to kind of connect to API, external APIs and things like that. Okay, so we're up to the next demo now. So in this scenario, instead of kind of using a Chainlink price feed, we're going to actually create a smart contract that connects to an external API. So in this case, I'll probably have to fix this import again, but we're creating a contract called API consumer. And in this case, we're kind of using this Chainlink client library here that we're importing. And in this case, we're creating a bunch of different variables here. So we've got a volume, unsigned integer, an oracle, and this is of type address, we're calling it oracle, and a job ID and a fee, right? The job ID is a 32-byte string. The fee is a unsigned integer. So in our constructor, which is the function that runs when we first create our contract, what we're doing is we're calling this set public Chainlink token function that we get from the Chainlink client here. And this basically tells our smart contract what the address of the link token is on the network that we're on. So in this case, it's Coven, and it will kind of reach out and it can kind of go, okay, for Coven, this is the address of the link token. So in the Oracle and job ID fields, what we're actually doing is specifying which job we want to use for this API request and what the Oracle contract is for the node fulfilling that kind of runs that job. So there's an Oracle contract, which is basically a smart contract that sits between other smart contracts and a Chainlink node. And it kind of acts as like a middleman that kind of takes requests, passes them to a Chainlink node, gets responses back from a Chainlink node, and then kind of, passes them back to smart contracts. So you can get these two values depending on what you're trying to do. In this case, we're doing a very simple API request. But like I said before, you can go to market.link and you can find all types of jobs here, depending on what you want to do, and you can kind of get job IDs and Oracle contracts from here. But for the purposes of this demo, we'll just stick to this pre-existing one here, which is just does a simple HTTP GET and kind of converts it to an integer, I think. So next, further down, we have a request volume data function that we've kind of created. This is a public function, and in this case, we're returning a 32-byte string, which is a request ID. And all we're doing in this function is we're building up a request object here, and we're calling it request. We're storing it in memory here. You could specify memory or storage. Sometimes you need to specify one or the other, but in this case, we're just specifying memory. And in this case, we're calling the build Chainlink request function, and we're passing in the job ID that we specified above to say, hey, we want this job to kind of do our API call for us. We're passing in the address of our smart contract here to say, hey, this is where kind of we want the response to come back to. And then we're calling what's called the fulfill function. So this basically means what is the function in this smart contract that we want to run when a response, when we get a response, basically. So if I scroll down here, you'll see we actually have a fulfill function defined here called fulfill. So all we're doing in the request is saying, hey, when you get the result of our API call request, send the response to this function here. Okay, so once that's done, we just have to set a couple of other things. So in our request, we're saying the path. So, sorry, I should have gone through this before. Over here, we're actually saying we have to specify what is the API call that we want to make. So in this case, we're saying we want to do a HTTP GET, and I can actually take this URL and paste it here, and hopefully you guys can see that. And here is the JSON that's returned. Let me just, volume 24. So we're saying we want to access this API. And over here, we're saying, what is the path that we want to traverse down in the response to find the piece of data that we want in our API call? So we want to go down the raw.eth.usd.volume24hour. So you can kind of see raw, ETH, USD, volume 24 hour here. So this is kind of the data that we want in our API call. So going back to Remix, the only other thing we want to do is once we get a result, once again, because we can't handle floating point numbers, decimal points, insolidity, we want to multiply the result by 10 to the 18 to get us a nice padded out response. And then once that's done, we want to send the Chainlink request to the Oracle contract, and we're going to pay the fee that's defined up here. So the fee is 0.1 link. So every job that you kind of request or want to kind of do some work for you, you kind of have to pay a fee in the form of link, because the Chainlink node is providing a service for you. You can think of it as kind of gas as well. And in many cases, they have to then write a transaction to the blockchain to kind of post a result to you, and that costs them ETH in the form of gas. So that's kind of why we have the fee here. So in this case, it's 0.1 link. So we're going to send that request to the Oracle contract. The Oracle contract will grab it and say, okay, no worries. It will then emit some data to the blockchain, and then the Chainlink node that runs that job will then see that data and go, okay, here's a job for me to run. It will perform the API request. It will get the result that we want, and then it will send the result back to the Oracle contract. And then the Oracle contract will then go, okay, they wanted to call this fulfill function now. So I'm going to call the fulfill function, and it's going to pass in the volume, the result that we got, and we're going to just store it in the smart contract here. So it's kind of like a request and receive model, where in your smart contract, you make a request, a Chainlink node gets that request, and then in another transaction, subsequently, it will then post a response, and it will come back into your smart contract. So it's not an instant thing like with the price feeds. It's a multi kind of step thing that takes place over multiple transactions. So I've just compiled that example there. And like before, we deploy it to injected Web3. So the difference with this smart contract to our price consumer one from before is we actually need to fund our contract first before we can kind of call this request volume data. We need to send a link to it because if I try on it now, you see I get this gas estimation error. It's because there's no link in the smart contract, and we need at least 0.1 link to send to the Oracle contract when we make the request. So what you do is you press the copy button here to copy the contract address, and then you go to your MetaMask, and in your assets you should have link, and you go send. You paste in the address of the deployed contract, and you can put 0.1 link. I'll just put 1. We only need 0.1 though. And we'll wait for that transaction to confirm. And then once that transaction is confirmed, we will then try to call our request volume data function. Coven seems to be a bit slower now.
While Harry's sending that transaction, really good question. A couple people asked, hey, what happens if the APIs or the aggregators, what happens if the APIs that these aggregators get their data from go down? What happens then? And this is exactly why Chainlink is a decentralized network. If one API goes down, it doesn't really matter, right? Because you have several other decentralized different entities providing data, right? And this is why decentrality is so important, so that we can continue having our trustless smart contracts and not ever have to worry about a single centralized API. So what we're showing you guys here is a way to get to get data from a single API. But what you would want to do is actually combine this with multiple APIs. Colin asked a great question, then a great follow-up, but not everything has so many APIs. And this is actually really important when you're designing your protocol, right? If something only has one API, then there's a good chance that that is going to be a centralized service. And you just need to keep that in mind when architecting, right? If you want to have a truly decentralized application, then yes, you're going to need multiple APIs. If there's only one API, well, you can build your application, but it's going to have that centralized component.
Yeah, definitely. So now if I go to Coven.etherscan and put in my contract address, I can see that my link token transfer is complete. So I can now call the request volume data function, and I'll confirm that transaction. There we go, confirmed. So what we'll do now is we'll wait a few seconds, because like I said, it's a request and response kind of design pattern here. It's not instantaneous. So the Oracle needs to receive the request, it needs to process it, send a response back, and that's another Ethereum transaction. And then kind of we'll get the response back in our smart contract. So I'll call the volume function now, and there we go. We've got a value here. So I can go back and compare that to this value, and we should kind of have the same value just multiplied by 10 to the 18. So there you have it. There's an example of a smart contract that accesses an external API using Chainlink, using a simple HTTP GET. As you can see, it's literally just a few lines of code, and you can connect your smart contract to external data, and it's really easy. And then once you have the data on chain, you can do whatever you want with it. So now we'll put it over to you. We'll go to the next exercise, the Any API exercise. Have a bit of a play around. We'll give you about 20 minutes. And if you have any questions, reach out in the chat if you're in YouTube sessions, or if you're in Zoom, put your hand up and hopefully an instructor can help you out.
Hey guys, I wanted to show something really quickly because I can't do. Harry, can I steal the show for a second?
Sure. Just give me a sec. I'll stop sharing.
Oh no, I can just steal it. I have so many tabs open. So a question that we're getting a number of times. People are saying, "Hey, I'm getting this weird abstract thing." It says, "Hey, this is an abstract contract. Like you can't actually do anything." So here's what happens. So when you choose like a wrong contract, well, I shouldn't have two of those there. I should do this, right? Oops, sorry about that. Oh, and I have another issue.
The word import. Yeah.
Okay, cool. So if I go to this deploy thing here, right? You actually choose the contract that you want to deploy. So if I choose like link token interface or something like that, I hit deploy. Can you guys all see this pop up, this alert, or no?
Yeah.
Okay, this contract may be abstract, not implemented. So that just means you've chosen the wrong contract. So if you get that error, just come back over here and you're going to want to choose the contract that's the same one as the name that we're here. So this is API consumer. So we look over here and we go, okay, that's going to be API consumer. So if you guys get that abstract thing or anybody else gets that abstract thing, please point them in the direction of being like, hey, on the deploy tab, you have to change contract to API consumer. So thank you for bringing that up, everybody who ran into that. Harry, back to you, my friend. Harry, you mind if I steal it from you one more time? Appreciate it. Sorry. And then one more thing. So a couple people said, hey, cool, great. How do I fund this? How do I fund the contract with Link? Well, once you hit deploy, you're going to see this contract down here. And this is going to be a step that you're going to want to get used to. And this little button here in your contract, you're going to click it. That's going to copy the address. And then in your MetaMask, you're going to hit send. And you're going to paste the address in here. You're going to change from ETH to Link. And then you can send how much Link. I think 0.3 is probably, plenty. Next, confirm. And then once this transaction goes through, then you're good to go. So that's how you do it. All right, back to you, Harry. Thank you.
Just so that we don't run too much over time, guys, we're going to continue at 1:45 Eastern time, so in a little bit over 10 minutes. And if you're still working on this exercise, you can kind of continue on it in kind of the last exercise. There's one more after this.
Remember, again, if you are having trouble and like you can't get your contract to work, raise your hand and we will DM you in the in the chat, and I can kind of come help you troubleshoot whatever's going on.
If you're getting a volume returned of 0 and you've done that request volume data function, maybe wait a few seconds and try again. So if you tried straight away, it could be that the Oracle callback just hasn't happened yet. So give it 20 seconds or so and then try it again.
Hey guys, I just had a really interesting question I wanted to share with you as well. Somebody asked, hey, what is that Chainlink or that API consumer is Chainlink client? What is that doing? What's going on there? And what's happening there is that when we do that import thing at the top with that @ symbol, we're actually taking a chunk of Solidity and just sticking it into our contract. That's all that import is doing. We're taking a whole bunch of code and importing it into our Solidity contract. Now, in our contract, when on that line, this contract API consumer is Chainlink client, what that line is doing is we're saying, hey, the name of our contract is going to be API consumer, and it is a type Chainlink client. So is Chainlink client, this is Solidity's way of doing what's called inheritance. So we're inheriting all of the functions and all the stuff from that Chainlink client code. So that's how our contract knows that it can call all these, Chainlink functions. So is Chainlink client is how Solidity does inheritance. And that's why we're importing that code in the first place. So great question.
Just for a great question, couldn't this contract be exploited in order to make it run out of link and then make it unusable? Yes, that's a great question, and definitely a serious consideration that you need to take when doing your smart contract development. You always need to be aware and think, what can other random people do with my smart contract? Should they be able to do that? And kind of come up with everything and kind of deal with all the security aspects needed to kind of protect some of these unwanted scenarios from happening. But we'll get into that more on day 3 on Friday, which has a specific section on smart contract security.
I had a quick question.
Sure.
Yeah, sorry. Could you? Oh, actually, yeah. Go ahead, Ari. Sorry.
Yeah, it's just why did the price feeds that we did in the previous exercise not require any link as a payment?
Oh, do you want me to jump on this? Yeah, I'll jump on this. Yeah, so basically with the price feeds example, that has actually already been requested by somebody else. So the price feeds are this fantastic tool because they're basically this pooled resource, right? Or this kind of like commons, if you will, where the data has already been requested and the Chainlink nodes have already returned it to this price feeds contract for you to go ahead and view. So that's why. So when we're doing the API call, we're doing kind of the smallest unit of like a price feed. So you can kind of think of a price feed as many APIs being called, being reported on chain, and then we can just go ahead and call it later on since the prices have already been aggregated. Does that make sense? Oh, wait. Oh, sorry. Yeah. Can people hear me or am I?
Yeah. No, that was great, Patrick. Thanks.
Okay, cool. Sorry.
All right, guys, we're going to move on now because we're nearing the end and we have one more exercise. So once again, if you're behind, try and catch up at the end. So Chainlink is more than just price feeds and accessing any API. Chainlink provides the ability to do off-chain computation as well. And one of the more pressing needs for off-chain computation was to implement a verifiable random number generator. Now, random numbers have existed for thousands of years, whether it's flipping a coin or rolling a dice. The goal is always the same, to kind of leave the end result up to random chance. And these random number generators in a computer are similar. They're an attempt to achieve an unpredictable random result. So until now, getting random numbers on chain has kind of been an issue, because the previous conventional way was to rely on-chain things such as hashes or using centralized APIs to kind of get randomness on chain, which like we discussed earlier, can be prone to being manipulated and hacked and things like that. And we actually see exploits happen with randomness too, not just with DeFi and Oracle attacks and things like that. People actually exploit smart contracts that kind of use randomness when they don't kind of use a really secure source of randomness in their smart contracts. So Chainlink VRF, or verifiable random function, provides a solution to generate provably random numbers. So this means that the on-chain contracts that request random numbers, when they get a random number back, it's actually a verifiably random number. So we use kind of math and cryptography to actually verify that the random number that the consuming contract gets was generated in a provably random way with the specified seed. And a seed is basically a source of input for a pseudo random number generator. And in the case of Chainlink now, it's actually automatically comprised of a number of things, such as the public key hash of the Oracle, which we'll get into a minute, and the hash of the block containing the request and things like that. But the general flow of how it works is you have a smart contract that says, hey, I need a random number for my game or for whatever. We have a smart contract that kind of gets these requests and then passes them on to a Chainlink node, a Chainlink node that can process the VRF requests. The Chainlink node will generate the random number using the seed, using some of the other inputs and stuff like that. And it will send the result back to the it will get back to the calling smart contract eventually. And the fact that it gets back to the consuming contract means that it's been verifiably proven to be random. So it's verifiably proven that it was generated by the Chainlink node that has that public key, and that it was generated with the seed that was given to the Chainlink node as well. So we know for 100% certainty that the random number that was given back was not something that was picked out of thin air to influence whoever's running the Chainlink node. It was actually created using the seed, and it's verifiably random. So there's a number of interesting use cases already using Chainlink VRF in production. One of the more popular ones that I like is minting NFTs with provably random traits. And gaming is a really big use case too. Randomness in gaming is literally blowing up. So many use cases, things like Avagotchi, lots of kind of examples you can kind of look up. So this is our last exercise. We're going to go through and we're going to deploy and interact with a smart contract that uses VRF to get a source of randomness on the smart contract. And it's very similar to an API request, the API call that we just did actually. The difference is that we're kind of generating a random number request instead. So we're importing the VRF consumer base library here that we want to use. We're creating a new contract called random number consumer, basing it on the VRF consumer base contract further up. And in this case, we've just got 3 variables we're defining. The key hash, the public key of the Chainlink node on Kovan, fulfilling the VRF requests, the fee that we're going to pay to the Chainlink node for the VRF request. In this case, I think it's going to be 0.1 link. And the random number result that we're going to get back from the Chainlink node to kind of, so we have the source of randomness in our contract. So in our constructor that runs when our contract is deployed, we're basically calling the VRF consumer base contract here, and we're passing in the VRF coordinator address here and the link token. So the VRF coordinator contract is the contract that sits in between smart contracts that want randomness and the Chainlink node that fulfills the randomness request. And the link token is the address of the link token on the specified network. So these can actually be obtained in the Chainlink docs. So if you go to docs.chain.link and you go to the using randomness section, in the contract addresses subsection here, you can kind of go to the Coven network here, and you can see here's the address of the link token. Here's the VRF coordinator for Coven, the contract. Here is the public key hash of the Chainlink node fulfilling these random number requests, and the fee needs to be 0.1 link. So all of these details in this example, we've taken from there. So here's the key hash, and here's the fee that we're specifying, and here's the coordinator, and here's the link token. So they're all getting set over here in the constructor, and like the API contract and the kind of request and response model that we went through before, it's very similar here. So we've got a requesting function called getRandomNumber, and it's a public function. And all we're doing in here is this just does some validation to make sure that your contract has enough link, and it will throw an error if it doesn't. But it's calling this request randomness function from the VRF consumer base library, and it's passing in the key hash and the fee to say, hey, we need a random number. So that will go to the VRF coordinator contract. The VRF coordinator contract will send the request to the Chainlink node. The Chainlink node will do the random number request, send the result back to the VRF coordinator contract. The VRF coordinator contract will verify that it's that was created with the seed that was generated when it sent the request to the node, and that it was generated by using the node's public key, and it wasn't some kind of imposter node or anything. And then it will specifically look for a fulfill randomness function in your consumer contract. So you need to call it fulfill randomness. And in this case, we're going to take in a couple of parameters. The second one is going to be our random number. And all we're doing in this case is ignore that. That's part of the bonus exercise. But all we're doing is we're just storing it in the smart contract. So I'm compiling that one like we've done previously. Then I'm making sure my environment is set to injected Web3, that the contract selected is your VRF consumer base. Make sure it's none of these libraries here. Sorry, ignore that. Make sure it's your random number consumer contract here and not any of the libraries. And you can hit deploy on that one. Confirm the transaction in MetaMask. Cool. And once that's confirmed, you'll get your deployed contract in Remix once again, just like with the API, the price feed, and the other contract. Once again, before we can do the request for, in this case, it's external computation, we need to fund the contract with Link. So I'm going to follow the steps again, like we did previously, and I'm going to send, in this case, one link to the contract, even though it only needs 0.1. If you can't remember how to do those steps, check out the exercise. It should go through it line by line for you. And once the contract is funded, we should be able to call this getRandomNumber function successfully. So I've called that. If I call the random result getter function here, we can see the result is 0 because we haven't got a response yet. Like I said, it needs to go to the VRF coordinator contract. The VRF coordinator contract needs to send it to the Chainlink node. The Chainlink node needs to do the work, get the random number, send the response back to the coordinator contract, and then back to our contract. So multiple steps. But if I wait a little bit, you can see I have a nice long random number here, which I'll paste as a comment here now. So you can use the modulus math function to kind of chop and change it if you want it to be between 0 and 100 and things like that. But for now, for just the basic demo, we'll get you guys to just create this smart contract, request randomness, and kind of get the result back and save it. So that's it for the demo. We'll pass it along to you guys to now do the final exercise. Once again, if you're in the Zoom sessions and you have an issue, raise your hand, check your DMs in the chat to see if you get a DM from a helper with the URL to join. Or if you're in the YouTube sessions, definitely ask in the chat and we'll try to help you out. Thanks. We'll give you guys 15 minutes on this one because we're pretty much at time, and then we'll spend just a couple minutes wrapping things up.
So some of you guys are going deep. I'm seeing a couple people saying, hey, what's this raw fulfill random method? It's used kind of by the backend, if you will, some of the other contracts, and it will call that fulfill randomness function. Good question. Going deep. Love it. And then people are saying like, oh, how is fulfill randomness being called? It doesn't seem like it's being mentioned anywhere in our code. Like what we saw with the API consumer, we said this fulfill.selector. What's actually happening is in that VRF coordinator address, right? You know how we're at the top, we're doing random number consumer is VRF consumer base. We're importing a bunch of code, and that VRF coordinator contract actually calls, and in that code, it calls fulfill randomness. So that when the Chainlink node responds, it actually responds to the VRF coordinator, which will then call fulfill randomness. So it's a couple steps there. In my mind, I always just think the Chainlink node is actually calling fulfill randomness, but it's really calling the VRF coordinator, which is then calling fulfill randomness. So good questions. Set public Chainlink token is a built-in function that says, hey, on the network that we're on, the Chainlink token is X. So it's picking the Chainlink token. So sorry, Harry, you can go and play the music. I keep jumping in.
Oh, good. The quality answers are much more important than the music.
But the vibes.
Hi, I have a quick question. How the randomness in Chainlink is guaranteed, and how we can compare that, to any random function in any of the languages, let's say Python. So what's the difference between the guarantee in that randomness and the randomness in Chainlink?
Hey, sorry, if you can raise your hand, we're answering a bunch of questions, so we'll get to it. Thank you. Raise your hand or ask in the chat, and we will get to it in a timely manner. Hey, James, if you want to join that link I just sent you. Hey James, I see you talking, but I can't hear you. You gotta join that Google Meet that I sent you. Yeah, somebody asking about how is it verifiably random? How is it different from just like JavaScript's math.random? When JavaScript actually calls math.random, it goes to some place in memory and picks something and says, hey, this is random enough, right? But the blockchain is deterministic. So if we go to a place in memory, it's not actually going to be very random at all, right? We know the state of the blockchain. We can't actually get a truly random number in a blockchain. So what the Chainlink node does is it gets a random number outside of the deterministic system, right? It gets it in the real world. The difference is once it returns it, it uses some cryptographic magic involving like the key hash that we saw of the node and the blockchain itself to actually prove the number is truly random. So there's a lot of intense what's going on behind the scenes. Hold on, I gotta mute Mr. Joe here. There's a lot of really cool stuff going on behind the scenes. If you guys want to check out the contracts that actually check and verify that the number is really random, everything's open source and on GitHub. So good question.
Mike, how can we see in Etherscan whether the callback to fulfill randomness has completed? So you can look at the Chainlink VRF coordinator address and put that into Etherscan, and you can look to see if it's posting randomness data back, and you should find a transaction that matches to when you sent your request.
Looks like most of you have finished, so we'll wrap things up now. Melody, do you want to take over for a minute before I wrap things up?
Yeah, sure. I mean, I already put it in chat, but I'm sure nobody saw it. So let me just share my screen. Okay, I'm taking it over, apparently. So we just wanted to thank you for being here for, I think, like over 3 hours now. And Harry, if you can send the Mentimeter link again, if you guys can rate us, we would be super happy. And we like that this creates a word cloud and it looks good when there's like so many people. And we also want to know how we can improve this because we have 2 more days of this and we want to give you the best experience ever. So we're going to be sending you the event survey out tonight, or maybe it'll be in the event invite. And also, let me just try to maybe see if the results are coming. Yeah, so I don't know if you guys can see it. Let me just zoom in. Now I can zoom in. God. So this is so fun, right?
Awesome.
So, yeah. Oh my God, we have like 40 people and joining. So what this does is that if like, let's say great, the word great is used a lot, it's gonna get bigger and bigger and bolder. So we see that as one of the top 2 words right now. Awesome, informative, amazing, interesting. So wow, 73 people, 76. So yeah, and we know that you're out of time and I'm just gonna stop sharing right now, but I can also share this link with you so you can check out for yourself. We just hit 100, almost 110 people. All right, I'm so happy for this. And I'm going to stop sharing now. So Harry, you can take it away.
Cool. Thank
Thanks
you.
for joining, everyone. Yeah.
All right, guys, let's wrap things up because we are slightly over time. So where are we at now? We've completed day 1 of the developer boot camps. You had a brief introduction to blockchain and smart contracts. We looked a bit at Ethereum and Solidity, as well as the Oracle problem and Chainlink. And we had a look at DeFi and Chainlink data feeds, and we had a look at accessing APIs using Chainlink and using Chainlink VRF. And in between that, you did some exercises. We did some playing around in Solidity, in Remix, creating your first smart contract. And then we kind of deployed and interacted with subsequent smart contracts that kind of use some of Chainlink tools and features. And hopefully this gives you a decent understanding of blockchain, smart contracts, and Chainlink, as well as some stuff in Solidity, working in Remix, and also deploying to a public testnet. So it gives you a bit of a flavor of what's it like to do kind of some basic smart contract development, as well as some basic smart contracts that use Chainlink. So thank you for joining. We'd love to get your feedback. So we'll send out some feedback forms, as Melody said. Tomorrow, we're going to be doing mostly exercises. So there'll be less presenting, less of me talking, more doing. And we're going to dive into using development environments. So on Wednesday, some of you will be in a session with Patrick and some will be with myself. And it's going to be really fun. There's going to be lots of hands-on. And you guys are going to get a real taste of what it's like to use some of the development environments that some of the really big projects in DeFi and stuff like that use. So it's going to be awesome. So once again, thank you for joining. We really had fun teaching this to you. We hope you got something out of it. And we hope to see you on the session on Wednesday. Thanks, everyone.
Thanks, everybody.
Thank you.
And then a huge congrats to everybody who's new to the space, who took the courage to say, hey, you know what, I'm going to show up. I'm going to go to this. I don't know anything about Solidity. I'm new to smart contracts. I have that imposter syndrome. Huge congrats to you guys for showing up, giving it a try, and then making it this far. For a lot of you, this is the first time you've deployed a smart contract, that you've coded some Solidity, and you should feel incredibly, incredibly proud of yourselves and really excited, ready for Wednesday, where we're going to even dial things up and go even farther. And like what Harry was saying, go into really being true smart contract engineers and doing exactly what the professionals do. So really proud of you guys. You should be incredibly proud of yourselves as well. Welcome to the space and excited for Wednesday.
Thank you for your time.
Thank you.
Thanks all.
Bye, everybody.
Last
Thank
question.
you, everyone.
Do you have recordings for Wednesday? For this? For Wednesday. Sorry.
Yeah, so with the recordings, we'll try to get them out to everyone, but I'm not sure if we'll get them out before Wednesday. But if we can, just keep an eye out on your email. Depends on a couple of things. But definitely, if not, then at the end of the 3 sessions, all the recordings will be made available for people that signed up for the bootcamp.
Thank you.
Thank you.
Thank you. Will the slides be made available by chance?
Yeah.
The slides, same as the recordings. We'll try to get them made available, but if not, definitely at the end of the 3 sessions.
Thank you very much.
Thanks, guys.
Thank you.